the Zephyr Zero, the compressed air powered motorcycle. My name is Robbie. I'm going to ask my fellow presenters to introduce themselves.
I'm Graham. I'm Tony.
Tanya.
Dallas.
I'm Ben.
And as Dr. Agarwal has mentioned, Simone isn't here today for a family emergency. She's actually down in Southern California. So, what we're going to go over today, we're going to review a little bit about what we've done and what we went over in the last presentation. Explain a little bit about the frame design and the research we've been doing. Tanya and Graham are going to then explain some of the engine and motor research and design that's been going on. We're going to update you guys on our Gantt chart, what we're making on our progress, and then go into future work and conclusions. So just for a review, again, we are building a compressed air powered street legal motorbike for urban transportation. We have our essentially our design parameters that we're designing around. We're aiming for a range of between 10 to 15 miles, which is typical for inner city urban transportation. A weight of 175 pounds, which is we're really aiming for low weight to maximize our range. The engine design that we've come up with is a custom rotary vane that we're building and designing ourselves. I'm going to talk a little bit about our chassis, our frame design. We're using a custom steel tube, and we're going to incorporate carbon fiber components wherever possible to decrease weight where we can. And again, because it's designed for urban transportation, we don't necessarily need a very high top speed, so we're aiming for a 30-mile-an-hour top speed to help increase the range that we can get out of our electric motor, or compressed air motor. So a little bit about frame design. There are many different types of motorcycle frames and chassis designs that are out there. The three main components of the main designs that are widely used are the monocoque design, the twin spar, and the space frame design, the multi-tubular space frame. So with the monocoque design, it can be used with many different types of component or materials, but the most common one is carbon or some sort of composite material. The benefits to this are twofold. It's extremely lightweight if done correctly. It can also be made to be very stiff. So these are used oftentimes in race bikes and very high-end motorcycles because of those characteristics. However, it incorporates a lot of cost and a lot of complexity in the design. It also doesn't allow for a lot of design flexibility moving forward. You essentially have to design everything from the start, and as soon as you design your molds and everything, you're set with where you're at right there. The other design at the top right is the twin spar design. This is one of the more common designs for common street bikes and motorcycles nowadays, more mass market. The reason for it is it's low cost, it's a very simple design, and it can be used with lightweight materials, typically aluminum in this case. And so it's very simple. However, it isn't necessarily very stiff, it's not very rigid, and it limits you a little bit more, or it limits you in terms of your packaging constraints for packaging all your drivetrain components because of how the design has to be incorporated. The third design that we looked at on the bottom here is a multi-tubular space frame design. And the benefits to this design are it can be made stiff and rigid in all load cases, and if done correctly, it can also be made to be lightweight. It essentially combines all the benefits of the monocoque design, not as efficiently as the monocoque, but at a much lower cost and a much lower complexity. But the biggest benefit for it is in the customization and the flexibility of the packaging constraints. So because we are custom designing our compressed air motor, and the packaging of the drivetrain components and the motor itself is going to be consistently changing throughout the design process, steel frame design is more beneficial to our applications because we can more easily adapt it to the changes that are making to the motor package later on in the design cycle. And then the next slide essentially is a summary of what I've explained to you. This is what we used to make the decision for our frame design, a design matrix if you will, but it's more of just a visual guide. It kind of explains the pros and cons, and this is what we used to come up with what we wanted to move forward with in terms of our design for our chassis and for our frame. So using this chart and using everything we've researched, we're going to move forward and use a space frame, steel space frame, multi-tubular design. One of the other reasons for it is a couple of us actually have a good deal of experience working with steel space frame structures, and so there's a large learning curve with making structural carbon components for the monocoque, as well as manufacturing constraints with the twin spar design. And so the space frame design that we have is more to our needs and more to our skill sets. So that's where we're deciding to go. And I'm going to pass it off. Tanya and Graham are going to explain the engine and motor research.
Alright, so the main focus of powertrain over the course of phase 2 was to lock down the engine selection. We were lucky enough to meet a group of chemical engineers that actually race an air-powered little car, and they were gracious enough to kind of let us use one of their gas air-powered motors and take it apart and examine it. And it was something that was really exciting because something we didn't really come across in our initial research. We've seen with a rotating cylinder, but we haven't seen a stationary rotor vane motor before. So I guess a big key component to the design is right here. It's a stationary motor. It's offset, eccentric to the housing diameter, and there are these vanes. It's hard to see, sorry, but there are little vanes that come out, they push out, they hold themselves against the chamber, and it actually makes multi-chamber expansion chambers as it rotates around the engine. So basically, we narrowed down our engine decisions to 3 types of motors: a single cylinder, a Wankel rotary, or a vane rotary. Wankel is the triangle that you see in like the RX-7 motors. As you can see, we really lean towards the rotary simply because this main point of we have more intake cycles per revolution versus a single cylinder. So we rated it on all the merits that we thought were the most important to the efficiency of our motor. We used a single cylinder as our baseline since it was something that all of our teammates were most knowledgeable about and were able to rate against. And lo and behold, vane rotary won. Another reason, a big discussion that we had was we do want to implement an expansion chamber. We'll explain a little later on why that'll be, but it'll actually increase the frequency of which we have pulse waves coming through the expansion chamber, but they are going to be of lower magnitude. So now that we had decided on the design of our engine, we needed to do a couple rough calculations to start to pick some parameters and constraints on geometric features mostly. We start with just what we thought would be simple thermodynamic equations to get shaft work. So we start with our known volume, which is an 80 cubic foot scuba tank, that we want to have our working pressure be 3,000 psi. We calculated that we would have enough energy to go up to 9 miles at the full speed limits, our maximum speed of 30 miles per hour, the entire time. And somehow we got to be a very low temperature of 174 Kelvin, which is about negative 100 degrees C. So we realized that there were some errors in the way that we had gone through our thermodynamic calculations, and the biggest part is we can't model the air in the tank as an ideal gas. We are 8 times past the critical pressure of air, hence it is now a real gas. So we had to go outside of our thermodynamics book, outside of anything we've ever ventured into before, and look at something called the Joule-Thomson theory. And unfortunately, everything is found experimentally. There are no tables for properties of air, anything past like 1500 psi, and we're double that. So therefore, we decided to go ahead and find it ourselves. We set up an experiment. We brought in an 80 cubic foot tank, and we released it to ambient, since we have no idea the actual pressure differences that we're going to have throughout the rotary vane quite yet. So this would be the most extreme case that we are going to see. And instead of the 174 Kelvin, which would be way below us, we ran about 248 Kelvin at steady state temperature. We used a thermocouple and an Arduino board and ran our tank out in about 3 minutes, which is about negative 25 degrees C, which relatively, is still very cold, but not nearly the negative 100 degrees C. So we kind of started feeling out where our inlet temperature is going to be and what our motor is going to have to do. And now we can kind of base our geometric dimensions around those parameters and find our ideal shaft work.
So, from all the research and calculations and stuff that we did, it showed us that the geometric features, how they affect the motor output, and those are based on the number of vanes, the vane thickness, the rotor diameter, the housing diameter, and the eccentricity. So our calculations are still ongoing. We're still trying to determine all the interrelationships between the geometric features, and that will eventually constrain our final design. So this graph here shows the volumetric efficiency versus how many number of vanes we have. On the top here, there are 4 vanes, and on the bottom, there are 8. As it can be seen in the graph here, although the volume change with the 4 vanes is a lot larger per chamber compared to the 8 vanes, the 8-vane motor is more efficient. The volumetric efficiency is increased because there are more number of chambers, even though there's a smaller volumetric change per chamber. Sorry. And we also did some calculations between the 4 and 8 and found that there's a 10% increase in the volumetric efficiency from going from 4 to 8. However, the more vanes that you have, the higher the friction is going to be. So, meaning we're not going to get as much work output. So we need to find a balance between the number of vanes versus the volume per chamber. And here's our Gantt chart, a little update of what we've got going on. So on November the 3rd, we're going to be doing our preliminary engine design, try to constrain everything down, get all the housing diameters, rotor diameters, and whatnot. A week later, on November the 10th, we're going to have our preliminary frame and suspension design. And by November 30th, we're going to try and have all the designs complete. And so just piggybacking on top of that, for our future work, we have to determine our packaging constraints, finalizing our engine design, finalizing the frame design, the suspension design, and a jig system, which we will use for testing. As Tanya was saying earlier, the air that we found was at about negative 20 or 30 degrees Celsius, which is really cold. So we want our operating temperature to be a little bit higher than that. So we're going to design a jig which will be able to hold an expansion chamber, which will allow some heat transfer to occur to heat up the air that we're going to be using. So this is just a very rough kind of jig idea that we've got going on. It's going to have the arms going to be able to move up and down to accommodate different sizes and everything. And these are going to be little clamping things that will be able to accommodate different diameters for the expansion chamber. And to conclude, we gave you guys our review of our goals for our project. We decided to go with a multi-tubular space frame design. We decided to pick the vane rotary for our engine, and we also calculated some of those parameters, although some are still underway. And we also presented our phase 3 due dates with the engine and frame designs. And here are some references.